May I have your attention? So now is the second session of today. My name is Choma from Boston College. I will be chairing this session. The first speaker is Professor Longju from MIT. He will talk about chiral superconductivity in Rhombohedral graphene.
Okay,
Welcome.
good. Thanks, John. Okay, good. First, I'd like to thank the organizer for having me here. I know it's a beautiful season around, and I'm going to tell you about chiral superconductivity in rhombohedral graphene. And we have two nice talks in the morning telling you the basics of Moiré, superlattice, Moiré effect, and the many beautiful physics there. I completely agree with Alan and Phi. Moiré is really a powerful tool. But for my talk, I want to zoom out a little bit. Before I get into Moiré, I want to start from a more general picture. So these are the people who contribute to the data I'm going to show you. This is my group at MIT, and my postdoc Zheng Guang is on his way to a faculty position at Florida State University in Tallahassee, and graduate student Tong Han, they are both here. So if you have technical questions, they are probably the better person to ask. And we got support from Liang Fu on multiple works on rhombohedral graphene, including the one I'm going to tell you today. And we also get nice HBM crystal from Japan. So I want to zoom out a little bit from a particular system and ask how to get emergent quantum phenomena in condensed matter systems. Okay? We know there are two very good examples. You get very ordered, microscopically robust quantum phenomena. One is called superconductivity. The other is called quantum Hall effect. And they are good examples of electron correlation topology. And through the decades of experience in condensed matter, we sort of know the basic ingredient you need to have correlation effect being promoted is to get some flat electronic band. Okay? And Moiré is one way that helps you to get there. And the other essential ingredient, as Alan told you, is this barrier phase, barrier curvatures in general for different topological systems. And they have told you that with 2D materials, you can assemble Moiré superlattices and get the large superlattice period to further control the property of electrons from individual layers. And I was also enlightened by the conventional wisdoms that in crystal systems, before Moiré, you have very robust chemistry and chemical bonds, and they already give you a flat band. They give you correlation topology. And we know the two systems both have advantage and disadvantage. The advantage of the conventional wisdom is chemistry is very reliable. Chemical bonds are on the order of several EVs. And every time you grow the crystal, if you control it well, you get very repeatable result. But the disadvantage is very hard to tune. Once the crystal is grown, you cannot dial something called a gate to tune its property. Well, 2D is good in that sense. You can gate tune it. You can have very rich structures assembled. But sometimes it has inhomogeneity, especially when you have Moiré between two layers that's of the same kind. So in the twisted bilayer graphene system, Elizaldov's group has used this nanosquid probe to visualize the variation of the twist angle. And turns out, because the angle is magic, if you are slightly off the magic angle, you lose the magic. And then this, microscopically, the property of across this twisted bilayer graphene is actually not that homogeneous. So I want to combine the advantage of these two wisdoms and develop a system that we can already have flat band and strong correlation effect, and we can make it more interesting by proximatizing it with additional ingredient, for example, Moiré superlattice, to make it more interesting. Okay? And the goal is to get correlation topology. And the 2D crystal I'm going to show you is really part of graphite. If you take exfoliate graphite and you get a few layers thick graphene on the silicon oxide silicon substrate, you can tell that there are regions with different contrasts. And that's simply proportional to the layer number of carbon you have there. But it turns out the structure of graphite or graphene multilayer is more rich than just having different layer number. There could also be different stacking orders. For example, these are the two leading stacking orders when you have more than 3 layers. Okay? One is known as Bernal stacking or ABA stacking. And this is the most stable form of graphite. 80% of graphite is in Bernal stacking. There's another stacking order known as rhombohedral stacking, which is not as stable as Bernal, but it's also local minimum in energy. It's the second most stable form of graphene layers. It's also known as ABC stacking. Okay, it's metastable. It's probably 10% of graphite is in rhombohedral. Well, this rhombohedral graphene or graphite is actually extremely interesting for flat band and topological physics. Okay, first let me convince you that in experiment we can indeed detect different stacking orders. The one way you can do that is to do Raman spectroscopy, and you look at a particular Raman peak that is sensitive to the phonon structures, which is depending on the stacking order. You can tell the ABA and the ABC regions, like what Tony did more than 10 years ago. And if you can map the whole flake spanning a few hours, you'll be able to tell where's ABA and where's ABC. And when I was a PhD student working with Fan Wang, we sort of took another approach by using infrared light coupled to an AFM tip. So we get the spatial resolution down to 10 nanometers, and we can also tell the two stacking orders apart because they have different infrared conductivity. Our most recent development in seeing stacking order, instead of indirectly determining the stacking order by using some spectroscopy, is to just use an infrared camera made out of InGas instead of silicon. You see, this flake is 4-layer, tetralayer. It's homogeneous from the visible channel. But if you look at with infrared light, within a second, you can tell where is AB, which is Bernal stacking, and where's ABCA, which is rhombohedral stacking. Okay? So this is really the game changer that allows us to very efficiently produce rhombohedral stacked graphene sample, although it's metastable, and in most of the cases, when you transfer it, it changes to Bernal. But you have a very fast turnaround feedback from the fabrication process, so eventually you can still beat the probability. Okay, so now we know where's rhombohedral. Why is rhombohedral interesting? Rhombohedral, if you look from the side, has this kind of staircase structure. And you can think of this as a big molecular, and all the orbitals in the middle kind of hybridize, form bonding and anti-bonding state. So they are not relevant for the lowest energy band structure. What's really relevant are these two dangling bonds. They are degenerate, and that give you 0 band gap. And they also give you this very funny dispersion relation where energy is proportional to momentum to the nth order, where n is a layer number. As you can imagine, if it's a monolayer, it's just a linear Dirac. If you crank up the layer number, very quickly, you get more and more flat band for free. There's no moire. There's no twisting. Okay? And this structure has another advantage, which was actually pioneered by Alan too. In 2D, it's really hard to give a talk without citing Alan's work. That you can further tune the band structure by applying a vertical electric field to break the symmetry between A1 and the Bn. As a result, you can open up a band gap at where the band is already flat, and you can make it even more flat by squeezing the bottom of the conduction band. You get even bigger density of states corresponding to this flat part here. Okay, so crystalline graphene has electrically tunable flat band. On the other hand, this structure also gives you a lot of tunable barrier curvatures because the band crossing points, topological objects, right? 5-layer graphene has a barrier phase of 5 pi per valley per spin. By opening up the band gap by gate tuning, you can also control the barrier curvature distribution in states near the band edge. And graphene has K and K prime value. They are time reversal pairs, so they always cancel each other if you populate K and K prime equally. So we think this is a good system to look into. At that point, there's not much prediction of correlation of topology in such kind of system. And here I'm showing you our early work on 5-layer rhombohedral graphene, ABCAB. Okay? And before we introduce moire, it was actually pretty interesting already that we have several works by Tonghang and Zheng Guang that we got signatures of correlation and topology in the absence of moire. Well, what probably catches the most attention is when you introduce a moire superlattice between graphene and the HBN with a moire period of something like 12 nanometer, almost 0-degree twisting, you get the so-called fractional quantum anomalous Hall effect that I believe is mentioned by our speakers, and also probably Xiaodong will talk about tomorrow. In our case, we observed so far a total of 8 fractions. I'm showing 7 of them now. That you see, these all follow the so-called Jane sequence. At the 0 magnitude, you get plateaus in RxY, and you get dips in RxX. And this is robust, persists to an electronic temperature, not exactly 10 millikelvin, but probably 20, 30 millikelvin. Okay? So Moiré is indeed very powerful. And this phenomena in rhombohedral graphene HBM Moiré has been reproduced in 6-layer version by a group at Peking University, and in 4 layers by us and Andrea Young's group at Santa Barbara. So this is a family of FQAHE materials. Okay, that's Moiré. The rest of my talk is going to be about no Moiré. Okay, as I said, without Moiré, you already get flat band, you already get barrier curvature. So why don't we look what happens in the absence of Moiré, more like the conventional crystal wisdom? And what we found there is some superconductor. And it's actually somewhat a magnetic superconductor to fit the theme of this workshop. And we think phenomenologically, this superconductivity is different from any superconductor that we can find from literature for the following reasons. Okay? As I said, there's no Moiré. There's no signature Moiré between graphene and HBN, so we have some big twist angle between graphene and HBN. And we have 3 devices. This one is very simple. There's no Moiré, there's no neighboring TMD, just rhombohedral tetralayer sandwiched by HBN. The other 2 devices do have a layer of WSE2, but instead of enhancing the superconductivity, it seems like introducing WSE2 actually weakens the superconductivity by lowering the TC. Okay? So I'm going to show you data from these 2 devices, and most of the phenomena of superconductivity are almost the same in the 3 devices. Okay, so this is from device 2, and you know the trick of tuning top and bottom gate voltage to control charge density at the horizontal axis and the gate displacement field to open up the band gap. Okay, so when you open up a gap with 1 volt per nanometer level of electric field, you get 4 regions that seem to go to 0 resistance, 1, 2, 3, 4. And later we confirm they are all superconducting. And this region here corresponds to when you have really flat band, bottom of the conduction band, and you dope electrons within that flat part of the band. Okay, and as I said, these are superconductivity, so as a function of temperature going down, you got different TC. The highest one is this big oval here, that's roughly 210 millikelvin. And I want to, point to you that these 4 superconductivity are already quite different at this level. If you see, SC1 and SC2 seem to be very fluctuating, right? So when I was telling you it's oval, well, it's roughly an oval, but there's fluctuation. There are kind of random jumps there. Well, SC3 and SC4 seem to be more normal. It's more homogeneous, okay? And this fluctuation is not only happening in the superconducting region, but also in a metallic region next to it. This is taken at the 0 magnetic field. And if you apply small outer-plane magnetic field, you can easily kill SC3 and SC4, which is similar to the superconductivity you got from other graphene systems, say bilayer graphene or trilayer graphene. But SC2 and SC1 are really, feeling something is going on. So then we did 2 things, okay? The first thing is that, we can park inside SC1. We choose a combination of density and displacement field and just watch it as a function of time. We measure the RxX as a function of time by doing nothing, no scanning of anything, okay? And we got this kind of temporal fluctuations. Most of the time, resistance is 0 in the superconducting state. Well, from time to time, it jumps, deviates from 0 briefly and come back, and this peak height varies from case to case. Okay, so it is a temporal fluctuation. It's not fluctuation triggered by you scan something. Secondly, you park in the same state, and now you scan the outer plane magnetic field back and forth, negative, positive, positive, negative, and you observe the hysteresis. Okay, what do I mean by hysteresis in a 0 resistance state? It's when you switch something there by the magnetic field, the whole thing becomes temporarily not superconducting, and you have a finite resistance peak there. And that tells you, scanning forward and backward, there's a hysteresis. Okay? And
both of those peaks are noisy? Both of those peaks fluctuate in time?
Well, I guess if you park there, it should be. But the time scale is another question, like, whether it's a few seconds or minutes scale. Okay. In this particular case, you have to probably wait a few minutes to see a jump like that. But we sort of understand how to make it more noisy.
Okay.
Yeah.
Is it my eye that is it negative?
Oh, okay. So this is some measurement issue. We confirm it's really 0. This is probably when the phase of lock-in was not set perfectly. We're pretty sure it's 0. Okay. And so basically, we're talking about the magnetic hysteresis, or switching between two superconducting states. And I'll tell you what these two superconducting states later. And as you can see, when you apply something like a 100 millitesla, much bigger than what can kill the SC1 and SC2, instead of killing the superconductivity, you stabilize it. Okay, remember, SC1 and SC2 have a lot of fluctuations. And there's also fluctuation nearby. With 0.1 Tesla beyond this cohesive field, everything got stabilized. There's no more fluctuation anymore. It's really like a magnet that you polarize in one way, and it just stays like that. But if you go to 0 magnetic field, thermal excitation can, from time to time, flip it. This is why we think this is somewhat like a magnetic superconductivity. Okay?
Perpendicular field?
That's perpendicular field. That's right. Okay, now let's moving on, right? We want to understand what is going on at the Fermi surface. The first thing we did is to apply an outer-plane magnetic field of 1.5 Tesla and measure the quantum oscillation. What you can learn from the quantum oscillation is, based on the density of electrons from one peak to another peak, you can tell the degeneracy of your Fermi surface, okay? And I will tell you what that really means later. Well, we have quantum oscillation reasonably well defined here with a very small period, while the period in other regions are bigger. I'll tell you what this period means later. And the second thing you can do is to ask, for this metallic state, even at 0.1 Tesla, you can probe its property, right? You can probe its resistance and probe its anomalous Hall resistance, okay? And clearly, this is a region that has a lot of anomalous Hall resistance, because the normal Hall resistance is at this color level at the same density, okay? And we confirm this is anomalous Hall because when we sweep the outer plane magnetic field back and forth, we also get the magnetic hysteresis to the right, which is here, and to the left of SC1. So the superconductivity, at least SC1, seems to be wrapped around by some magnet. And this magnet coupled to outer plane field and has hysteresis. So we think this points to a picture that, related to the so-called isospin symmetry that can be spontaneously broken when you have flat band. In graphene, we know there are spin up and spin down. We know there are K and K prime value. So there are a total of 4 copies of any band structures at the single particle level. Well, if nothing interesting happens, all the 4 pockets are populated equally, and the anomalous Hall will cancel each other because there are time reversal pairs populated at the same time. However, when your band becomes really flat and the exchange energy is important, the degeneracy of these 4 pockets could be lifted in certain ways. For example, you could get a half metal, means 2 out of the 4 is populated, or you can get a quarter metal, which means 1 out of the 4 is populated. As you can imagine, if you have 1 out of 4 populated, then most naturally you have spin and value polarization in that pocket. Then you have a net barrier curvature and anomalous Hall signal. And experimentally, I was showing you quantum oscillation. The period of quantum oscillation here actually corresponds to a quarter metal because we can just count. Lambda levels has a well-defined degeneracy, right? It's a quarter metal. It has anomalous Hall. So it feels like this part, at least, is a spin and a value polarized quarter metal. And the superconductivity is right next to it, okay? So you may wonder, is the superconductivity also stemming from a spin and value polarized pocket? That feels really weird because that gives you big momentum of a Coupe pair. And also means the spin is polarized, so it has to be a P wave, at least. Okay? Let me show you what we have now. So this is cutting through SC1 as a function of density, okay? To the right-hand side is that quarter metal, spin value polarized. And we're applying a very simple idea. If I apply outer plane magnetic field, I'm coupling to the orbital magnetic moment of the quarter metal. If the neighboring state, superconductivity, is not magnetic, or not as magnetic as the quarter metal, then I would expect the boundary between them will shift towards the superconducting side, because the quarter metal is more favored at finite magnetic field. Okay? Well, what we really see is that on the right-hand side, this boundary remains pretty much vertical in both Rxx and Rxy. And that tells us immediately this superconductor itself is magnetic. Almost, or maybe exactly as magnetic as a quarter metal. And on the left-hand side, the lower density side, it's even more dramatic that the superconductivity, instead of being killed or eaten, it actually expands towards lower charge density. Which means if you do a line cut here, if you park at the charge density, which does not show superconductivity at zero magnetic field, it will actually become superconducting when you apply some magnetic field. And that also indicates the superconductivity couples to the magnetic field in a way that you expect a magnet does. Okay? But still, this doesn't answer, because we don't have quantum oscillation inside the superconducting region. This doesn't really nail down what is the apparent state of that superconductivity. Now let me show you more data. Okay? One thing you can ask is, how about above TC? Okay, when the superconductivity is gone, do you have any signature of time versus symmetry, value polarization, or anomalous Hall? And the answer is yes. Okay, this is 480 millikelvin. This dashed line outlines the two ovals, SC1 and SC2. You have clear anomalous Hall both inside and outside the superconductivity region 1. And you do have magnetic hysteresis when you sweep the outer plane field back and forth. The star and the square are both inside the superconductivity state 1. And there's clear jump, and there's a hysteresis loop. And if you cut at B equals 0, you got spontaneous time versus symmetry breaking and non-zero value of Rxy. As far as we understand, this is the only pure material that shows magnetic hysteresis and anomalous Hall above TC. And you can watch as a function of time. For example, you stay at the star position, which is inside the SC1 region, right? And you cool it down. You see above TC, you got a magnetic hysteresis in Rxy. As you cool down, of course, once you get into the superconducting state, you just measure a 0 Rxy, right? It gets shorted. But you still have this hysteresis with the field back and forth, just like the one you see in the Rxx channel. Although the background, normal Hall and anomalous Hall signal are both 0. Okay? And you might notice that when I draw this dashed oval here, there seems to be a boundary that's kind of intercepting into it at 480 millikelvin. That's a real observation. Let me tell you what that boundary is. Okay? So this is showing SC1 and C2, and there is a boundary at 480 millikelvin. You may think, okay, this just intercepts the SC1, but not covering the whole SC1. And we know this side is quarter metal, right? Through quantum oscillation, this is quarter metal. Then you may feel, okay, so maybe only this little slice of SC1 stem from quarter metal. But that's actually not true, because this boundary, this yellow dashed line here, actually will shift as a function of time. If you do a line cut at a constant displacement field, for example, here or here, you can tell this side is a quarter metal. This kink here corresponds to the yellow dashed line. At high temperature, it's at a relatively high charge density. While when you cool it down, it actually shifts to lower charge density. And then SC1 develops to the right of this boundary. So the quarter metal somehow is going to extending to lower charge density, and superconductivity is only residing to the right of it at both line cuts. Okay? So this gives us more confidence that the parent state of SC1, at least, should be thought of as a spin and value polarized quarter metal. Okay? And another thing I want to bring to your attention is that when you see this outer plane magnetic field dependence, you probably have noticed that, wait a second, it's a very weak superconductor. It's only 200 millikelvin. But it can persist to outer plane magnetic field almost 1 Tesla. This is totally unusual. So the thing you can do is to, based on that out-of-plane critical field, you can just use BCS to estimate what is the coherence length. Of course, that may not be appropriate because this is most likely not a BCS. But if you do that, you'll get a coherence length on the order of like 20 nanometer for SC1. And you can compare that to the interparticle distance, which is drawn here as the dashed line here. And you find that SC1 has a coherence length that's really close to the interparticle distance. And that brings us to this BCS-BC crossover picture where the superconductivity is close to the crossover, but still on the BCS side. Okay, while other more trivial superconductor have, is deep in the BCS side because the coherence length is much longer. Okay, so what can we say about this superconductivity? These are the observations. Okay, you get the magnetic hysteresis in the superconducting state below TC. You get anomalous Hall hysteresis above TC. And these are just unique observations of this superconductor compared to other superconductors. And if you believe this is a spin valley polarized parent state, then it has to be, finite momentum pairing, right? And it has to be chiral because it breaks time versus symmetry, not just by the spin, but the valley, the orbital motion breaks time versus symmetry. So time versus symmetry is broken at the orbital level, and this distinguishes it from the so-called ferromagnetic superconductors people find in heavy fermion system. And what we do not know yet at this point from experiment is whether this is topological, right? It has to be px plus IPY instead of p to be topological, and we don't know what the pairing mechanism is. But I want to remind you, this is a simple carbon. There's no moraine, there's no TMD, there's no SOC. It's just flat band. Okay? And I should point out that after the experiment, there are already several theory works looking at these problems. And if you just read the title, you find that it seems people agree that this is chiral and possibly topological. This is our one of our organizer Liang Fu's work that does show this calculation compatible with experimental observation. There's a phase winding of the other parameter. Okay, so this is probably the last slides I'm going to show. That, as I said, if you believe it's a single flavor, then it cannot be S wave. It has to be P wave, and then it could be either PX PY or PX plus minus IPY. Well, the thing is, these two electrons making the Cooper pairs are from same valley, and there's already an orbital level angular momentum, so it's already chiral. And theorists has been teaching me that, okay, so if you are already chiral at the atomic orbital level, then most likely that angular momentum or magnetism is going to couple to the other parameter and choose from px plus IPY and ps minus IPY corresponding to the k and the k prime value. And that will make it topological if the pair is not too tightly bound, which I don't think we are in the BC limit. Okay? So with this, I just flashed these slides. Okay? We're working on Rhombohedral graphene. There are many phenomena out of it. And the idea here is we want to understand the essential ingredient and to add more flavor into it and see what we can build. Okay? With that, thank you for your attention.
Thank you so much for the beautiful talk. Fazil.
I speak loudly, so thank you. Thanks, John. Maybe you showed the data and I didn't see it. The transition, the superconducting transition at zero field was very wide, right? With the width of the transition being almost the same as the actual transition temperature.
You mean this?
That's right. I would like to know how that looks like when you apply field. Does that width become narrower, or does it stay that wide?
That's a good question. I don't think we have measured that yet.
Especially if this is a superconductor that's established or maybe better promoted by magnetism. I think that would be very interesting to see that kind of
Yeah,
data.
we would love to do that.
So in your fluctuation, time fluctuation plot, so there are also some plateau formation with finite resistivity?
So I can tell you what we are thinking of this fluctuation or plateau thing or spikes thing. If you think the superconductivity could be in the k valley or k prime valley, then it's fine that you can have a domain 1 in between. Okay? Maybe what the thermal activation does is to trigger some domain 1 motion that makes the sample to switch from being polarized in the k valley to k prime valley. And when you have a domain 1 that's kind of intercepting the path from source to drain electrode, that domain wall doesn't have to be zero resistance. And maybe that's what these spikes are. And we know experimentally the normal state of this superconductivity have a resistance on the order of 2 kilo ohm, while all these spikes and fluctuations are much smaller than that. So it doesn't feel like it's the whole thing become non-superconducting.
All right. The last question.
Have you looked into the in-plane B field dependence?
We're working on that. Yeah.
Oh, okay.
Can I ask you a question? Yeah, it flashed towards the end, right? That there are by now many experiments on different layers of thickness of
Yes.
Rhombohedral graphene, and in the future, what will be the best thickness
Okay.
to explore?
I wish I can tell you that the thicker the better, but so far we have explored the 4-layer, 5-layer, 6-layer. These three are, in many senses, very similar. Fractional quantum numskull and maybe superconductivity in the phase diagram are very similar. I do not know exactly what happens if you go to much thicker than this, because I think Geim did some experiment back in 2020, shows a 10-layer rhombohedral or thicker than 10-layer. The correlation effect there seems to be weaker than in this. And we sort of, at the single particle level, have some understanding why that may be the case, because the k to the nth dispersion is not perfect. Okay, that's when you neglect a lot of hoppings. But when you do include them, you get this trigonal warping, you get more subtle features. As you can see, the band is already becoming something like a Mexican hat. Although that's more for the valence band than the conduction band, but if it's too thick, I suspect that may kill the flatness of the band. So it may not be like the thicker the better.
Thank you so much, Long.
Yeah.
Let's move on
Thank you.
to the next speaker.
There should be one there.
And do you want to walk around?
Maybe.
Okay.
Why it doesn't show? Well, it shows the non-slide mode. Well, I'm sorry for the technical problems, but I have nothing to do with it.
I have to turn that on from back there, but you can
Okay.
just put it on your belt for now.
What?
I'm gonna have to. Let's see if we recognize it now. Yep.
Okay.
Okay, try it again.
Let's see what this recognize the slide mode. Yes, it does.
Okay,
Thank you so much.
great.
Let me-
So